In this video, we discuss Bayes' theorem. Bayes' theorem is a theorem that describes probability of an event based on prior knowledge of conditions that might be related to the event. And here at the beginning of this video, I want to distinguish between what we learned before about conditional probability and Bayes' theorem. Imagine that you have an experiment that can be performed in two steps, step A and then, or it has two stages, stage A and stage B. If we are asked to find, if we want to find probability of B given A, that means we want to find the probability of the outcome, the second stage outcome, if the event A has already done. This is called conditional probability. So conditional probability asks about the final outcome, or the outcome of the second stage or the final stage, if the prior outcomes, in the previous stages, is known. Now Bayes' theorem, almost the converse of this. Bayes' theorem, if the experiment can be performed by two steps, Bayes' theorem talks about probability of the prior event to occur if we know the result or the outcomes, the final outcome. So here we find probability of A, of the prior event, given the later outcome is known. So this is Bayes' theorem. So this is the difference. Conditional probability asks about B, the outcome, given the previous event has occurred, and Bayes talks about the probability of the previous event, the occurrence of the previous event, given that the final event or the event in the next stage has occurred. Let's start with the following introductory example. In this example, we are given three machines. We have three machines, A, B, and C, and they produce 45%, 30%, 25% respectively of the components, but of the total production. But some of these components or production do not meet certain specifications. For the production of the first, for machine A, that do not meet certain specifications is 6%, and for the second, for B, machine B is 3%, for machine C is 4%. Now here the question is, one component is selected at random from the outputs and found to be defective. So it's defective. We know the final stage result or the final stage outcome. Now the question is, what is the probability that the component selected was produced by machine A? So we know the final result, and we're asked whether the first step came from machine A, or the first step is A, or the first machine, or the machine that produced that defective outcome or output is machine A. So this is Bayes, because we are interested in finding probability of the beginning event. So here it's better for this type of problems, Bayes problems, to do tree diagram. So let's graph that diagram. We have three machines, A, B, and C, and the probability of choosing one of the outcomes of A is 0.45 because the probability, because machine A produces 45% of the total production, and for B it's 0.3, which is 30% of the production. For C is 0.25. Now machine A produces defective and non-defective. For non-defective we use defective complement to denote non-defective. D component non-defective, and D is defective. So the production of B is either D or D component complement. For C, D or D complement. Now what is the probability here in this branch? In this branch the probability is 6% is defective, so it's 0.06. So what is the complement of that? That means we have 90.94 non-defective come from machine A. From machine B we have 3% defective and 0.97 non-defective, and probability of the defective from C is 0.04 and non-defective 0.96. And actually this number here, this probability is probability of D given A, probability of defective, provided that that outcome comes from machine A. And this is probability of defective provided that it comes from B. This is defective provided that it comes from machine C. Now we want to find this probability. That means we want to find if it's defective. Here this is defective, this is defective, and this is defective. So we selected one component or output, and it was defective. Now our question is that what is the probability that that defective comes from machine A? So that means defective comes from A. So that's one branch. That's one branch, this branch. But this branch comes from how many branches? This branch gives defective, this branch gives defective, and this branch here gives defective. So we have a ratio. Probability of getting outcome or component from machine A, provided that or given that it's defective, is probability of, this is probability of A, probability of A times probability of defective given that it comes from A over all these branches. So the sum of all these branches, I mean probability of A times probability of defective given that it's from A, plus probability of machine B times probability of defective and comes from machine B, plus probability of C times probability of defective given that it comes from machine C. This formula gives us Bayes, this is called Bayes rule or theorem. It's conditional, but it's written in this form. It's part of all, and we are interested in finding the branch that under interest and then divided by all branches that give defective outcome. Now if we want to compute this, we get, now on this branch, the branch under of interest is 0.45 times 0.06 divided by probability of A times probability of D given A is the same, plus probability of B given probability of D given B is 0.3 times 0.03, plus probability of C is 0.25 times probability of B given C is 0.04. Now computing this, we get 0.58, approximately 0.58. If we want to understand this using Venn diagrams, this is the sample space, and this is the set of all defective outcomes, all defective outcomes here. So this is D, and we have three machines. A, machine B, and machine C, the production of machine of A, machine of B, machine of C. That means if the production is here, or the outcome chosen from here, that means it's not defective. If it's from here, then it's defective, and that's correct for B and C. Now here, this is defective and comes from machine A. This is defective and comes from machine B, and this is defective and comes from machine C. If we take the union of all these, A intersect B, D, B intersect D, C intersect D, we get the set of all defective outcomes. So here we are interested in one branch. That means we're interested in this. We are interested in this part of this whole part, Now another example, in a study to determine the annual income of married couples in which the husbands were the sole providers, and those in which husbands and wives have income or both employed, and we have annual family income. We have some categories. The first category, let's call it A. The second one, let's call it B, C, D, E, and F. And the married couples of each category is given, the percentage is given here. So for the category A, 4% are married, and for B, 10%, and so on. And here we have in the third column, the income comes from the employment of both, or both spouses are employed. That means we have 65% of the 4% of the married couples who have income 150,000 or more. So the first question is, what is the probability that a couple selected from this area has two income? So here we want to find probability. Let's call the two income, the event of getting couples who have two incomes, T. So probability of T, that means we have T comes from, we have probability of, let me do a tree diagram first to make it easier to understand this probability. So we have A, category A, B, C, D, E, and F. And then we have either both of them work or not both of them are workers. Here, both of them, not both of them. Okay, now probability of A is just 4%. This is probability of A is 4%, which is 0.04. And probability of T given A is obtaining T given that A has already done or occurred is 65. So this is 0.65. 65% or 0.65, and that we do this for all other branches. So here, for example, for B we have 0.1, and probability of T given B is 0.73. We have 0.21 for C, and 0.68, 0.24, and 0.63, 0.3, and 0.43, and we have 0.11 and 0.28. Now we want to find the probability of that the couples are T, or two of them have income. That means this, 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 and this, all these branches. So all these branches that give two outcomes or two incomes. So here we have probability of A times probability of T given A plus probability of B, this is the second branch, times probability of T given B, plus probability of C times probability of T given C, plus probability of D times probability of T given D, plus probability of E times probability of T given E, plus probability of F times probability of T given F. Now these probability, we just find the product, sum of the product of these probabilities. So that means 0.04 times 0.65 plus 0.1 on the second branch times 0.73 plus on the third branch 0.21 times 0.68. On the fourth branch we have 0.24 times 0.63 plus 0.3 times 0.43 plus 0.11 times 0.28. If we find the sum of these, we get 0.5528, and that's the probability that the selected couple has two income. Now for part B, if a randomly chosen couple has two incomes, so we know that the final result is a couple who has two incomes. What is the probability that the annual income of this couple is 150,000 or more? That means in category A. So we are asked to find probability of A given T, given that they have two outcomes. Probability of having annual income 150,000 or more, given that they have both of them have income. So we can apply the rule, the Bayes theorem. So this says probability of A times probability, and then we reverse the order of this probability T given A over same thing, probability of A times probability of T given A plus probability of B times probability of T given A, etc., until we get the last one, which is F. But we call this probability of T here. We call this probability of T. So this is probability of T. But we already computed this. Now probability of A times probability of T given A is the first branch. It's 0.04 times 0.65 over probability of T is, we already computed in part A, it's 0.5528, and then using calculator we get answer like 0.047. Now the last part C, asks if a randomly chosen couple has two outcomes, that means T already occurred. What is the probability that the annual income of the couple is greater than 49.999 or for 49,999? And that means here this is for 49,999. Greater than this, that means those four groups A, B, C, and D. So we want to find probability of A. Let me write it this way. Probability of A given T plus probability of B given T plus probability of C given that the couple, both of them are, the husband and wife, both of them are workers or have income. Then we add probability of D given T. So those are the probabilities that we need to compute, and then we know that this is probability of A times then probability of, we need to reverse the order, T given A plus this probability of B times probability of T given B plus probability of C times probability of T given C plus probability of D times probability of t given d. Now we need to divide this by probability of t, the total probability. So we divide by total probability of t. Now the first branch gives 0.04 times 0.65. The second branch is 0.1. The product of multiply of the probabilities is this. In the third branch we have 0.2121 times 0.68, and the fourth one is 0.24 times 0.63, all divided by probability of t, all branches. We already computed this. It's here 0.5528, and using calculator we get some answer can be approximated as 0.711.